Hello everyone, Sahil here. Today we will learn about the k nearest neighbors algorithm. It is the oldest and the most simple machine learning algorithm. It is also one of the most popular and effective machine learning algorithms. So let's just jump right in. So what is KNN? To give an overview of k nearest neighbors, first of all, it is a supervised learning algorithm. That is, along with our features, we also have our training labels. KNN can be used for both regression and classification. In regression, we compute continuous numerical output, whereas in classification, we compute discrete outputs like class labels. When it comes to KNN, for regression, we take the average, but when we have a classification problem, we take the majority vote. We will talk about this in a moment. Another idiosyncrasy of KNN which sets it apart from another machine learning algorithms and it makes it really interesting is that the training part is basically non-existent. It is a non-parametric algorithm. That is, there are no parameters to learn. At last, as I mentioned earlier, it is by far the most simple machine learning algorithm. So let's talk about the intuition behind KNN which actually validates that. You must have heard the quote that you are the average of the five people you spend the most time with. KNN follows the same principle, it follows the same rule. This is the assumption that KNN makes that different instances, different examples, which have similar looking features, they will tend to have similar labels. So if there is a test example and I want to predict a label for that, what I will do is that I will take that test example and I will find the examples in the training set which have the most similar looking features and I will see what their labels are and I will use that information to predict the label of this new example. So what is the roadmap? What is the procedure which KNN executes to do this? So for an unlabeled example, you start by calculating its distance with every other training example. Now that you have calculated these distances, you take k number of examples which have the minimum distance. In other words, they are the most similar examples to your unlabeled example. Now for classification, you have to take the majority vote. So for example, k is equals to 5, that is you have 5 examples and you have 3 examples of class A and 2 examples of class B. Then class A has the majority vote and your prediction will be class A. Now, if you are doing a regression problem, then what you have to do is that take the average of the k outputs, take the average of the k data points, and that will be your answer in that case. Now, here comes the important part. These things can really make or break your algorithm. These things are really important. The first is the distance metric. So, the distance metric is the metric that you use to measure the distance to compute the distance between two examples and it has to reflect that distance properly. So this is used to compute the similarity. It is computing the similarity between two examples, how similar they are, and if they are the same example, the distance will be basically zero. And if you have two examples and you are using a certain distance metric, but it doesn't really reflect the distance between those two examples properly, it is not accurate, then it will really mess up your algorithm and your predictions will be wrong. So you have to make sure that the distance metric you are using for your particular use case, it is the right distance metric and it is reflecting the distance between two examples properly and accurately. The second most important thing is K. What is K? K is the number of nearest neighbors that you are considering when making a prediction. When you are making a prediction, you consider some K data points which are the nearest, and K is the number of those data points. Now, its impact can be really significant, and we will talk about this in detail a bit later. The last thing is the magnitude of features. KNN is really sensitive to the magnitude of features. So, to explain this, let's say you are trying to predict a rent of some property, and you have two features for that. One is the square feet, and the other is the number of bedrooms. The first example says that it is 1000 square feet and two bedrooms. The second example says that it is 1500 square feet, and it is one bedroom apartment. Now, because the KNN algorithm, it doesn't really understand the concept of square feet and BHK. It will see and compare, it will process these two different features equally. And because the magnitude in square feet is in the range of thousands, and the magnitude in the number of bedrooms is in the range of 1, 2, and 3, it will prioritize more resources to the square feet feature, and it will tend to ignore the BHK feature because the magnitude is really low, which is counterintuitive and it is bad for your algorithm. So you always have to scale your features, and we will talk about it how to do this. The last thing I want to mention here is that the distance metric and k and other things that we will mention later, these are hyperparameters, and the hyperparameter tuning you are doing here is actually compensating for the training part. See, in other algorithms like logistic regression or neural networks, we actually devote a lot of time in the training process, which takes a lot of computation and time. But we didn't have any training phase here. We didn't train anything. So something has to be there to make the prediction. The hyperparameter tuning you do here, it compensates for that, and it helps the algorithm to make the prediction. So let us start with the distance metrics. So as I mentioned earlier, the distance metric is just a way of computing the distance between two examples, how similar they are, how close they are, what is the distance between these two examples. So if we measure the distance between the same two example, these two examples are the same example, then the distance will be zero because it is the same example. There are a bunch of different distance metric, and the most common one is the Minkowski metric. As you can see in the formula, let's say we want to compute the difference, compute the distance between two examples x and y, and both of these examples are n dimensional. So what we do is that we take each dimension of that example and we subtract it, and we take it to the power of p, and we sum all of them, and then we take the pth root of that. If you will put p is equals to 1, then it is just the subtraction of each of the features, each of the dimensions, and then we just sum it up. It is the Manhattan distance. When we put p is equals to 2, it is basically the Pythagoras theorem. It is also called the Euclidean distance. If you put p is equals to infinity, then it is basically the Chebyshev distance. Now which one you should use? It is basically a hyperparameter, and basically you have to see, you have to do the trial and error method, and you have to see which one works best for your example. The other distance metric, which is not that common, is called the cosine similarity. So if you have two examples a and b, and you want to measure the distance between them using this metric, what you do is that you take the dot product of a and b. What is the dot product? You just multiply each dimension of that feature with the other dimensions of the other example, and you divide it by the magnitude of these two examples. So what is the magnitude of a? The magnitude of a is basically take each feature of that example and square it, sum it, and then take the square root of that. Similarly, take the mod or the absolute value of another example b and multiply that, and just put it in the formula, and you have the distance. The cosine similarity metric is basically used when you have a lot of features, because when you have a lot of features, the Euclidean distance metric actually fails, and cosine similarity metric sometimes work really well. Again, I have to say, you have to try and you have to see which distance metric works the best for your use case. So let's talk about the next hyperparameter. This is also really important and it has a significant impact on the learning process. So what is K? So when you are about to make a prediction, basically what are you doing? You are seeing your nearest neighbors, and you are basically trying to contemplate that what is me? Yeah, who am I? Basically, you are seeing the others and you are trying to understand what you are. So you have this unlabeled example, this test example, which is comparing itself with other nearest neighbors. The number of those nearest neighbors is k. Now it can actually really make or break your algorithm, because this is really important. So let's say, let me explain you with an example. Let's say that you choose a really small value of k, but you were not supposed to do that. The real value of k that which had the best accuracy was k is equals to 7, but you chose k is equals to 2 because you don't know about it. But you, when you chose k is equals to 2, what happens is that you are considering less number of nearest neighbors. So let's say that because you are considering less number of examples, and those examples, basically the number of features in those examples, they overwhelm the number of examples. So you have to make a balance here, the number of examples and the number of features. There has to be a balance there. If the number of features exceed, then you will end up overfitting. But if the number of examples, that is the value of k, is exceeds a certain value, then you will end up underfitting. So these are two extremes of the spectrum, and you have to be somewhere in the middle where you get the best accuracy. So how will you find the best value of k? Because you have your own data set, you have your own objective, your own problem. So the value of k will vary and you have to find that out. And how will you find it? There are two methods. The first is the trial and error method. You might say that this is really random because k can be anything. So there is another method too, which is called the elbow method. What we recommend is that you take these two methods and you use them simultaneously, and it will speed up your process. What is the elbow method? How should you use the elbow method? We will talk about it later. The last thing I want to mention here is that always choose an odd number. K should always be an odd value. It should never be an even value. Why is that? Let's say you have two classes and you are trying to compute the class. You are doing classification. Now, because you have two classes and you chose even value, which was not recommended, you chose k is equals to 4, let's say. Now it can happen that you have two classes, and you have four examples that you are considering. It may happen that you get two examples of one class and two of another class. Now you are stuck. Now how will you make a decision? That's why, so that this thing doesn't happen, this situation doesn't occur, you should always choose an odd number, so that there is always a decision, there is always someone overpowering the other class, and you have a solid decision. Okay, this is our prediction, this is the class. Regarding the methods, especially the elbow methods, we will show you with an example how we implement that. So the third one, feature scaling. As I told you that KNN is very sensitive to the magnitude of features, and just because of a huge gap between the range of different features, then it can actually make your algorithm, it can actually make KNN prioritize some features over others just because of the gap in their ranges of magnitude. So you have to scale the features accordingly so that it doesn't badly impact your algorithm. As I explained you earlier, it will prioritize the 1,000 square feet feature over 1 BHK because it doesn't understand the concept of square feet and BHK. But both of those features are equally important when it comes to the prediction. And if it will prioritize the 1,000 square feet features, then it will end up making a wrong prediction. That's why we have to do feature scaling. Now, how do we do that? Let's say that each training example has n number of features. Now these n features will have their own different ranges, and you want to scale them accordingly. So what you do is that you have these n features, you take each and every one of them and you take the mean of these features. So across the training set, you take the mean of each feature. So now you have these n means of these n features. Now, let's say that you have this one feature which was square feet features. The mean would be in the range of thousands because all of the examples were in the 1,000, 1,500, 2,000 range. and you had this other feature which was the BHK feature, number of bedrooms. Now the mean of this feature will be like 1, 2, 3 in this range, right? Now you have the mean of each and every feature. Now do the same exact same thing and compute the standard deviation of those features. Now you have these n means and n standard deviations of the n features you have. Now, every time you take any training example or any test example, you take this mean value and standard deviation. What you do is that take that example and just subtract the mean of all the features from all the features of that example. So your example has n features and you just take all the n means in that sequence and you subtract that. So all of the features in that example have the mean subtracted from them. Now similarly, just divide this thing with the standard deviation, the n standard deviation of those features. Now all of your features have been scaled accordingly, and you will see that it will really improve your accuracy. You can just try it. Don't do feature scaling and implement KNN, and then implement feature scaling, then implement KNN. You will see a vast, you will see a big difference in the accuracy. And you always have to do it. Always do feature scaling when you are using KNN. Now, I actually just explained you the whole procedure how to do feature scaling, but you can actually just do it really easily using the sklearn pre-processing, the sklearn library. So you just import sklearn.preprocessing, you just import the standard scaler, and you import the standard scaler and use it to fit transform, scalar.fit transform, and give it the features, and it will return you the features with the mean subtracted and divided by the standard deviation, and it will do the job for you. So the best thing about this is that you are doing feature scaling. You don't have to learn anything. You just have to do this computation and it's done. Unlike the distance metric or the k, where you have to learn the values. Now that we have seen all these things, we went from introduction and I explained you the intuition behind the algorithm. Then we saw the steps KNN takes. After that, we saw the things that can actually make or break your algorithm, like the distance metric, K, and the feature scaling part, and the details as well, how you should implement it. And now, after that, we have seen all these things. We have the information and we are ready to implement KNN algorithm. So let's just start with the implementation. The first thing, of course, you will just load your dataset. So you can just load your dataset from the sklearn library if it's available. If it's not available in the sklearn library, you can just download the dataset and change your directory into the folder where the dataset is saved. Now that you have changed your directory in the place where you have saved your dataset, just use the pandas library and read the CSV. Just give the name of the CSV file, use the read CSV method, and create a pandas data frame out of that. You can see that the name of the pandas data frame here is df underscore reg. The reg means regression, because for now we are implementing regression, and you can also see in the dataset there are no labels there. There are only numerical continuous outputs, and it is the last one, the price. That's why we are using the regression part. We will implement the regression part because it's a regression problem. Some tips here: just make sure that there aren't any missing values in your data frame, in your data set, because it will just create problems for you when you are iterating. And just remove those examples if they have any missing values. The other thing you can do is that if for now we are doing regression, but if you are doing classification and you have labels, for example, cat, dog, and fish, so you have these strings. So just remove these strings and give a numerical output there. Replace it with 0, 1, 2, or 1, 2, 3, or anything you like. You can do it manually as well, or you can just use label encoder from sklearn's library, and it will do the job for you as well. Now after that we have loaded our data sets. The next thing we will do is that we will initialize our model. As I told you earlier that KNN can do both regression and classification. Now the sklearn library which we are using here has two versions of KNN. It has two versions of KNUS neighbors. One is k neighbors regressor and the other is k neighbors classifier. The regressor one is for regression problems, the classifier one is for classification problem. Now because we have a regression problem here, we will use the k neighbors regressor. Now first we initialize that and we use the get params method to see the parameters it has. Now let's just look at those parameters, the algorithm, the n neighbors, p weights. Now we will see in the next slide what we can change here, which maybe improves our accuracy, which maybe improves our model, because we didn't tell anything. We haven't told the algorithm anything till now, and the parameters that we are seeing here, all of these are default values. So let's see what we can change here and what all of these parameters actually mean and signify. Now let's start with the algorithm. As the algorithm was set at auto, what does it mean? We also have these other three options. What does all of these options mean? So the auto one basically means that, as it is self-explanatory, the auto one just decides for itself. Whatever the algorithm thinks is best for itself, it chooses that. Now if your use case is specific, you can use the other three options and it can potentially improve your accuracy. So the next option is brute. So as the name suggests, brute basically means that it uses brute force. It takes the unlabeled example, it takes that test example, and it literally compares that test example with all of the training examples. So it takes a lot of time, it takes a lot of computation. So if your use case demands that, if you want your unlabeled example to be compared with every single training example, if that's something important to you, you can use brute. Now you have other options as well. You have the KD tree option. So how is it different from brute or auto? So the KD tree option, what it does is that it doesn't compare the unlabeled example with every single training example. Before that, what it does is that it organizes and segregates the data into a binary tree. That way, you don't have to compare the unlabeled example with every single training example. Instead, what you will do is you will compare the unlabeled example with the training example, which really matter, which are important, which are significant for you. Now, this works really well only when the number of features is less than 20. If the number of features exceeds 20, I wouldn't recommend KD tree. Now, what should you do then? Well, you can use the ball tree option. The ball tree, as the name suggests, it it is different from brute force because it doesn't compare with every single example. But how is it different from KD tree? Now, the KD tree fails when the number of features exceed 20. But the ball tree works really well when the number of features is large, when it's more than 20. So what does the ball tree do? It segregates the data, it organizes the data into nested hyperspheres and it uses that information to make its own binary tree. So it's a bit more sophisticated basically. And you can use it if the number of features is more. So this was the algorithm one. We also had this other parameter named weights and it was set at uniform. So what does it mean? Basically, when you have like k nearest neighbors, let's say you have two nearest neighbors or four nearest neighbors, basically you are comparing them and you are taking their voting or in classification or you are getting their average. Now the impact each example has, each nearest neighbor had, is uniform only when you set the weights at uniform. You can change it and it can potentially improve your accuracy as well. If you change it to distance, the impact of each example becomes the inverse of the distance. So basically, if the nearest neighbor is more near than the other nearest neighbor, its impact will increase. So in classification, it will have a slightly bigger vote. In regression, it will have a slightly bigger number. Its impact will increase with the inverse of the distance. So if it becomes near, its impact will increase if you set the weights to distance. The other parameter that we had was n neighbors. So n neighbors is basically your k, the number of nearest neighbors. So a good rule of thumb here is that you can just set k is equal to square root of n. N is the number of samples in your training set. You can just start with it It is not necessarily the best value of k that you will ever need. Of course, you have to find the best value of k with the trial and error method and elbow method, and whatever fits for you. So that was n neighbors. The last one is p. So as I told you earlier that the most common type of distance metric is the Minkowski metric, and it has this p hyperparameter. So if p is equals to 1, it is Manhattan distance. If p is equals to 2, it denotes Euclidean distance. If p is equals to infinity, it denotes Chebyshev distance. So if you set p is equals to infinity there, or if you set p is equals to 1 there, it will change that. So you can use it to change it and see what works best for you. Now that you have loaded your data set, you have initialized your model, the training phase is the next part. Now, to be honest, the training phase is close to non-existent because KNN is a lazy algorithm. It doesn't like to do a lot of hard work. So KNN is like that student who doesn't like to study the whole year, and when the exams come and he really has to give some output, he studies on the last night of exam. So this is KNN. And the thing you have to do here is, regardless of the training phase, is that you have to split the data set into training set and test set. The training set is the part of the data set where you actually do the training. And the test set is the part of the data set which is untouched. You don't use it for training. You only use it for testing. That's why it is called the test set. Now that first of all you take your data frame and remove the price column because that is the labels column, and use the train test split function of sklearn to split your dataset into xtrain xtest and ytrain and ytest. Now you will see here that we have set test size equals to zero point 0.3. So this just signifies that the percentage of the training and test set is 70% and 30%. So it's easy. So the next thing you do is just call the fit function on the training part of the dataset, and after that just predict. Just use the X test and just start predicting, and just store those Y pred. Store your predictions. Now use those predictions and get the mean square error using the MSE method from sklearn, mean square error, and you can just see the mean square error, and you will use it to see which thing works best for you, which hyperparameter works best for you. So as I told you earlier that the accuracy of your model will depend on the hyperparameters you have chosen. The better your hyperparameters, the better your accuracy, the better your performance. So now I should tell you about the elbow method I was talking about. So basically, I told you that to choose the distance metric and to choose the value of k, basically you are doing a trial and error method. Now you should implement that with the elbow method because it will help you. It will speed up your process and you will just see that now. Now I want to point out one thing which is really good about KNN. It's that the training phase is close to non-existent. It doesn't take any time. It means that you can choose different values of hyperparameters and you can test them really quickly. You don't have to wait for the training to finish. Now we are implementing the elbow method for the value of k. So you can see that we started from the value of k from 1 to 51. Now this seems really bizarre, right? So many values of k. So you are training the algorithm 51 times from 1 to 50. Because the training time is close to non-existent, we can actually do that. And after the training, we predict and we plot that. We predict the values on the test set and we plot the error with the value of k. And this graph always looks like an elbow. That's why this method is called the elbow method. Now, what you should take out of this? You can see that the drastic change occurs between the values of 1 and 3, 1 and 4, right? After that, the values of 4, 5, 6, 7, there is little change. And after 6, 7, the accuracy actually starts decreasing. So this is the range. Just by looking at the graph, I am able to get an idea which value of k will work for me. Now when you run this code, you can just compare the mean squared error, and it actually tells you that the minimum squared error is at k is equals to 6. So the graph also tells you that. So now you have the value of k. Similarly, you can get the distance metric. Which distance metric gives you the lowest error. That's how you implement the trial and error method with the elbow method. This is how you choose your hyperparameters. Now you must have been really happy that there is no training phase. It is really fast. Now to compensate for that, you are actually doing this. You are taking different hyperparameters, you are looping over them, you are looking at the graph, you are getting the lowest value of the error, and you are seeing which one works first, which one works the best. So this is the part where you compensate for the training which the KNN didn't do basically. And even after that, one thing I want to mention here, as compared to different algorithms like logistic regressions, neural networks, they take a lot of time in training. But at test time, they take finite time. The test time is fixed, but it doesn't happen with KNN. KNN doesn't take any time to train, and for the test time, when it has to predict, it takes a lot of time because it has to measure out distances, and it gets the nearest neighbors and then give us the result. So that computation takes time. So if your training set is really large, it can become a problem for you because it will take a lot of time. So here are some other metrics that you can use to get an idea of your model, how good is it performing. So the first is the classification report, and you can just use the sklearn metrics and import that and just give it the needed things, the y test and the predicted and the target names, the classes you have, and it will just give you the classification report, and it will calculate all the things like precision, recall, f1 score, all of these things, and you can get an idea how your algorithm is performing. The other thing you can use to get an idea of your algorithm is the confusion matrix. Now when you have a lot of classes, you don't really, it becomes really difficult to get an idea what is happening here. So if you have 50 classes, and sometimes some class gets predicted with other class. So let's say I have 50 classes and all of them are 1, 2, 3, 4 till 50. And there is a class 7 which is getting confused with class number 45 again and again. So whenever class number 45 comes, it predicts 7. And then whenever class number 7 comes, it sometimes predicts 45. So these two are getting confused. Now, by just looking at these numbers, it will become really difficult for me to know that this is happening because there are a lot of classes. To counter that, you can use a confusion matrix because when you see this graph, you can see what is happening, which class is getting good predictions, which class is getting the most confused with which class, right? So this is another metric that you can use, the confusion matrix, and it is really useful. So like everything has its own pros and cons, KNN also has its own merits and demerits. And just look at them because these are important. See, whenever we have some target, some objective, whenever we have some result we want to accomplish, we think about these things because we want to make the decision whether we want to use KNN or not. And if our own interest match with the advantages and disadvantages, then we will use KNN. This will determine whether we want to use it or not. So what are the pros? So the first one you already know, there is no training time because it doesn't do the training, right? It's a lazy algorithm. The second one is that it serves as a good benchmark for more complex algorithms. So what do I mean by that? So let's say you have a lot of training data, thousands of examples, 10,000s of examples, and you are training a deep neural network, a really large network, and it is taking all of this data, it is taking a lot of computation from your part, it is taking a lot of your time. You just use KNN and get a good benchmark. You get a baseline that you can already get this. You can already achieve this level of accuracy without even training. So that you know that if you are using a complex algorithm which is taking so much of your resources, it should be better than the accuracy given by KNN, right? So it really helps to know what should be our target, what should be our expected level of accuracy when we are using more complex algorithms. That's why it helps us. It serves as a good benchmark. Now let's look at the demerits. So the first one, of course, is large phase complexity. because it has to store the whole training set. Because it doesn't do the training, and at test time when it has to predict the label, it has to compare and compute the distances. So to compare, it has to have those examples, so it has to store them. So if your training data set is huge, then you have to store that training data set, and it will be a problem for you, because sometimes the training data set is so large, it becomes infeasible for you to store it, and even compute time is not feasible. So the next disadvantage is that only large time complexity. Because if you have a big training data set, if you have a huge training data set, then not only you have to store it, but you also have to process that whenever you want to make one prediction. Because it's not like other algorithms like neural networks, logistic regression, they take a lot of time in training, especially neural networks, they take a lot of time. But when you want to predict, it is a finite time. It gives the prediction really fast as compared to KNN. But KNN, it doesn't take any training time. But if the training set is huge, it has to go through all the examples. Or if you are using other methods like KD tree or ball tree, still it has to go through a lot of examples. So it will take a lot of time. So the first one is space complexity. You have to store the training data set. The second one is time complexity, that it takes a lot of time to compute its prediction.